All right. All right. So, greetings, scholars. I see, people are kind of trickling in. I think I have a solution for the confusion as far as the room. I realized that when I set up um, teams, it's like basically you have to make repeating occurrences. So I did it for like Tuesday. So it's basically there are like two or three different events set up. So I probably after today I'm gonna like redo it. I was trying to avoid it because I didn't really want to mess with it since we got something that was kind of working. Um, but I might just redo them so it's only one. So it's only one room. Now that I realize that it's creating multiple rooms, or that it created like two rooms. I'm just going forward with the presentation because I loaded. It's really only two rooms. I loaded the course ID with the passcode, and the session is being recorded. So I know that you all can find it. You just had to kind of get into the room. I posted the meeting ID with the passcode, so but I'll try to get it to one room after today. Okay. So the goal for today, I think we introduced. Listen, last time we were working on this alternate chapter 8 with matrices and like these topics on solving a system of equations. So the goal for today, since we did three sections last week, we just need there are only two left in that alternate chapter today that we need to do. Okay. So we're continuing with this alternate chapter 8 on matrices and determinants, and we're going to be working on section. We're going to start with section 8.4, multiplicative inverses of matrices and matrix equations, and then you know, again, I'm going to do that thing where see how many slides we got today. Yeah, it's we'll do the best we can. I'll just monitor the time, right? So I'll honor the time. I'll let you all out on time, and but my intent is to finish all of 8.4 and all of 8.5 today. So idealistically, we can finish within time. But if we go over, I'll let you all go at the right time, and then I'll just finish the recording to get through the whole two sections. Okay. Welcome, ladies and gentlemen. I don't know about you, but for me, this is my Friday, right? This is my last one for the week. Then, I can just like, I always blank out, right? When I leave you all, I just, I'm either asleep or gaming or eating or like running around town, right? So that's just my nature, right? Okay. So I say that just because I'm a little bit geeked. I'm ready to start the, not to be on call. Anyway. All right, so let's look at this section. A few objectives here. So let me see. Last time, we introduced matrices. We saw how to convert a linear system of equations into what is that called? An augmented matrix. And then we first introduced the upper row reduced echelon form, where we had, through using the three row operations, we got ones along the main diagonal, and then we got the lower triangle to be all zeros, and we saw how to solve the system of equations with that form. Then the next step that we did, we took it a step further, where we had ones along the main diagonal, and then we went on to use that to get zeros everywhere else. And so that was called Gauss Jordan elimination method, right? So that's a method for solving a linear system of equations. Um, okay, what else? Oh, and then we saw some different types of solutions where, if we have either no solution and what that might look like, or we might have infinitely many solutions and how we capture all of those solutions. Okay, so we're kind of continuing that discussion. Again, we have two sections here. So a few objectives here. We like to find the multiplicative inverse of a square matrix, use inverses to solve matrix equations, and encode and decode messages. I think the last thing we kind of started working like matrix equations. So given a linear system of equations, we converted it into a matrix equation, and then we started kind of exploring how to solve matrix equations. It's similar to solving regular equations, but there are some things that you have to be cognizant of. And a lot of it really comes to pretty much doing things in a certain order, and being aware of like this, making sure that the sizes of the matrix actually work out. It's not a 100% direct correlation to regular algebra, but it's similar. It's extremely similar. Okay. So then here we want to look at the multiplicative identity matrix. Also, Let me see this as far as, I mean, the main thing is just kind of keep making your way through the assignments in my open math. That's the main thing. And just, as long as you get into this call, or at least, be in contact, just to stay on top of your attendance. Those are the main things I'm looking for. There was something else. I can't think of what the other thing I was trying to get out. Okay, I'm not going to worry about it right now. Yeah, let's keep going. So the multiplicative identity matrix. Oh, and the other thing was, just as usual, if you have questions, feel free to unmute yourself to get my attention, or feel free to type in the chat. I am monitoring the chat if you have questions. Also, yeah, I can be bad about like replying to emails again. When I'm not with you all, I'm just trying to keep my sanity. So if I haven't responded to an email, just ask me like at the end of class, like say, hey, can we like talk privately about whatever, or if you feel like it needs to be private, it doesn't necessarily have to be private. It's just whatever makes you comfortable. But yeah, the best is if I haven't responded by the next time we meet, just ask me during class. Ask me near the end of class next time we meet. Okay, or today, in other words. So the multiplicative identity matrix. The n by n square matrix with ones down the main diagonal from upper left to lower right and zeros everywhere else is called the multiplicative identity matrix of order n. This matrix is designated by I sub n. For example, I2 is a 2 by 2 square matrix with ones along the main diagonal upper left to lower right and zeros everywhere else. I3, you see it here. A 3 by 3 identity matrix where one along the main diagonal, zeros everywhere else, right? So multiplicative identity, that means we're going to be doing some multiplication. Identity matrices, usually that means like when you do the operation, you get back to that same matrix, right? Okay, let's see how we use this. Okay, so the definition of the multiplicative inverse of a matrix. Definition of the multiplicative inverse of a square matrix. Let A be an n by n matrix. If there exists the n by n matrix A inverse, such that A times A inverse equals the identity matrix and A inverse times A equals the identity matrix, then we say that A inverse is the multiplicative inverse of A, right? Okay. So when we have two matrices, to show that one is the inverse of another, basically when you say the first matrix times the second one, if you get identity, and then if you switch the order, right? Now then you say the second times the first, and you can get this, you still get identity, then we say that that second equation is the multiplicative inverse of the first. Matrix multiplication is not closed under is not necessarily closed. Is not necessarily commutative, right? So if we say the matrix A times the matrix B is not necessarily always equal to, if you switch the order, the matrix B times the matrix A, right? So that's one of those things that kind of gets a little bit, you have to check and make sure that things are working when it comes to matrix multiplication. If a square matrix has a multiplicative inverse, it's said to be invertible or non-singular. If a square matrix has no multiplicative inverse, it's called singular. Okay. So show that B is the multiplicative inverse of A. So in order for the matrix B to be the multiplicative inverse of A, what we need to show, we need to do A times B. We need to show that that equals the identity matrix. And then we need to do B times A and show that that also equals the identity matrix. Okay. Okay. Let's see it in action. All right. So let's start with the matrix A times the matrix B. Okay. So that's going to be 2, 1, 1, 1, like this, times the matrix B, 1, negative 1, negative 1, 2. Now, last time when we introduced matrix multiplication, we were like, we need to make sure that the order or the size of the matrices are proper so that we can do the matrix multiplication. So, for instance, the size of the first matrix is a 2 by 2. Size of the second matrix is a 2 by 2. So in order to do matrix multiplication, the number of columns of the first matrix has to match the number of rows of the second. And they do match, so we're in the clear to do our multiplication, right? So then when we go to do our multiplication, we always do the row times the column. We say the row of the first matrix times the column of the second matrix, right? So we can do this. we'll say, for instance, this row, come on, style, about like that looks good, like that, okay. So that row, and then let me copy, paste that row times this column. Style, let's go blue and blue. Okay, so I was doing the row times the column. Okay, so let's see. If we said the row times the column, that's gonna, I'll do the first one color coded, but then going forward, I'm not going to do color coded. Row times the column, so that's going to be 2 times 1 plus 1 times negative 1. 1 times negative 1. Okay, that's going to, so that answer is going to be our first entry. Then we say row times the column. Okay. So then the next entry is going to be 2 times negative 1. So we know we're going to have, well, let me just do this. 2 times negative 1 plus 1 times 2. 1 times 2. Okay. That's supposed to be blue. No, it's supposed to be, yeah, this is supposed to be blue. Style. Okay. Okay, so then we reset. So this guy resets to the first column, and this is now our second row. So we're going to say this row times this column. So we go green. It's going to be 1 times 1 plus 1 times negative 1. So 1 times 1 plus 1 times negative 1. All right, we just did the row times the column, and then for entry 2, 2, we use the second row times the second column. 1 times negative 1 plus 1 times 2. 1 times negative 1 plus 1 times 2. Okay, so then we're going to calculate each of those. I thought I would have enough space. I might have enough space. So that's going to be 2 minus 1. So that first entry is going to be a 1. Negative 2, let's see, negative 2 plus 2 is 0. Okay. 1 plus negative 1 is 0. And negative 1 plus 2 is 1, right? So that's one direction that we can confirm, right? So then we also need to show the reverse. When we say B times A, if we get the same thing, then that's what we're trying to show. I think this might be enough space. So I'm going to say B times A, and I'm not going to do the color coded this time. Let's see. So the row here, we can at least highlight the row times the column. Okay. So that first entry, 2 plus negative 1 is going to be a 1. Okay. Row times the column. Negative 2 plus 2 is going to be 0. Oh, wait a minute. I gotta switch it around. I didn't switch the order. Let me back up. See, that's what happens when you don't write things out. Let's actually let me write it here. So we're saying B times A, right? So I need to do basically just switch them around. I think I'm gonna just copy and paste instead of writing out. So let's copy, paste. So then B needs to go first. Space. So B is first, A is second, and we still need to make sure that we're doing the row times the column. So we're going to say the row times the column. Okay, I think I can just write the answer now. Okay, so if we say the row times the column, that's going to be 2 plus a negative 1, which is 1. Then it's going to be a 1 plus negative 1, which is 0. That's going to be what? Negative 2 plus 2, which is 0. Then negative 1 plus 2, which is 1. Right? So that's that also. So even when we reverse the order, we still got the identity matrix. So that's how we show that these two matrices are inverses of each other. Okay. Okay, let's keep going. All right. So then A times B, you see it worked out. They got the identity. And then when they did B times A, same kind of deal. We also got identity. So then multiplicative inverse of a 2 by 2 matrix. If A is this 2 by 2 matrix shown, then A inverse is going to be 1 over A times D minus B times C. And then we switch the places of A and D along the main diagonal, and we flip the signs along the other diagonal. The matrix A is invertible if and only if A times D minus B times C is not equal to 0. If that AD minus BC is equal to 0, then A does not have a multiplicative inverse. Okay. So this is a shortcut that you can use if you're given a 2 by 2 square matrix that's invertible. Let's keep going. Find the multiplicative inverse of this guy. Okay. So if we say A times D minus B times C, as long as it's not 0, then we can find the inverse, right? So from the previous slide, let's actually go ahead and find our AD minus BC. Okay. That's going to be a 3 minus 2, which is 1. Notice that that's not 0. So because that's not 0, this should have an inverse. And so that means A inverse, I'm just applying what was on the previous slide directly. It's going to be, in this case, it's going to be 1 over that 1 that we found times, again, we switch A and D. So this is going to be our 1. This is going to be our 3. And then we flip the signs of the other diagonals. This becomes a positive 2 and a positive 1. Okay. And if we distribute that 1, we essentially get what you see. The 1, 2, 1, 3. Okay. Now, let's see if I can get this to work. Okay. I think that'll work. I just want to show you this in the TI 83. What is this? 83 plus, right? Let me reload and refresh. Okay. So my matrices, let me think. Matrix is, okay, on the left-hand side of the calculator, there's an orange button or yellow, I guess orange, I don't know what color. It says second, and then below that is like teal green. I guess it says alpha, and then math, and then it says x to the minus 1. I'm going to hit second x to the minus 1 to pull up my matrix option. I'm going to go to the right to go to edit, and I'm going to put in my matrix A, right? Okay, so I'm going to hit enter. Now A is a 2 by 2 matrix, 2 by 2, okay? And then we have 3, negative 2, negative 1, and 1, okay? Now we found the inverse, but the calculator can spit it out in an instant, right? So let me go back, let me quit. Let me go back to matrix. And I want to call on the matrix I just typed in. So I'm gonna just hit enter to select number 1. And if I want to do inverse, it's a button on the left. It says x to the minus 1. I'm gonna hit that. And it should give us the 1, 2, 1, 3. That's one way that we can check. You see the 1, 2, 1, 3. All right. In the previous example, we could have also done this in the calculator. I'll have to just do them separately. But we just confirmed the one that we just did. If I go back to matrix, go to edit, our matrix A is a 2 by 2. It goes 2, 1, 1, 1, 2, 1, 1, 1. Okay. And then I want to go back to matrix, edit, and let me edit B, matrix B. Matrix B is also a 2 by 2 matrix. 2 by 2. Okay. And let's just type it in. 1, negative 1, negative 1, 2. Okay. So then now we're going to show when we do A times B, we should get identity. And when we do B times A, we should also get identity. So I'm going to go back to the home screen, clear. I'm going to go back to matrix. I want to say A, and I think I can just do matrix. I think I can just hit B so that it should recognize that as A times B. Let's see if we get identity, right? And then let's go back to matrix. Let's do B times A. Right? And you see it there. Okay. I just wanted you to be aware of that ability or that feature. I'm sure you can do matrix. You can do matrices in Excel or Notes. I use Numbers. It's like Numbers is basically the Mac version of Excel. But yeah, I just wanted you to see that. Okay, let's keep going. So we did it by hand. We confirmed these in our calculator. All right, we confirmed that result, so it should be good. 1, 2, 1, 3. Okay. Okay. All right, let's keep going. So define A inverse of for any n by n matrix A for which A inverse exists. First form the augmented matrix A bar IN, where IN is a multiplicative identity matrix of the same order as the given matrix A. Perform row operations on this augmented matrix to obtain a matrix of the form I bar B. All right, this is equivalent to Gauss-Jordan elimination to change A into the identity matrix. The matrix B is A inverse. Verify the results showing that A inverse equals identity and A inverse A equals the identity matrix, right? So similar to like in the previous section where we use the matrix row operations to, augment to solve the system of equations, we can use those same row operations to find the inverse of any square matrix that has an inverse, right? Let's see if we can see it in action. So notice this one is a 3 by 3, right? So we can use Gauss-Jordan, or we can use the row operations to find the inverse of the matrix here, okay? So first thing we want to do is write our augmented matrix. So let me see, we have our, let's see. So we got 1, 0, 2, negative 1, 2, 3, 1, negative 1, 0, okay? And then on the other side, on the right-hand side, we're going to put the identity matrix, a 3 by 3 identity. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So then the goal is, using those 3 row operations, we want to transform the left-hand side into the identity. And then when we're done, the right-hand side is going to become our the inverse, right? And just a quick recap, the 3 row operations at our disposal. 1, we can switch any 2 rows. 2, we can multiply any row by a non-zero scalar. And then 3, we can multiply any row by a non-zero scalar, add it to another row, and replace that other row, right? So, again, the goal is to, here we want to transform the left into the identity. So we've already got one part done where we have a 1 in the upper left. Now we want to use that 1 to get zeros below it, right? Okay. So if I'm going to use that 1 to get zeros below it, let me see. So first thing I want to do, I'm going to say row 1 plus row 2. I'm going to replace row 2. Okay. I'm going to say a negative times row 1 plus row 3, replace row 3. Okay. I don't really have space there. I'm going to resize this. I'm just going to write it here for now, below, and I'm going to resize it. So with this, row 1 stays the same. So we still have our 1, 0, 2, 1, 0, 0. Okay. So for row 2, we said row 1 plus row 2 replace row 2. So that becomes a 0. That's a 2. That's 5, 1, 1, 0. And then row 3, we said a negative times row 1 plus row 3 replace row 3. So this becomes a 0. This stays as a negative 1. That's a negative 2, negative 1, 0, and 1. Okay. So we achieved our first goal. We used that 1 to get zeros below it. The next goal is to get a 1 in the center location. I feel like the easiest way to do that, multiply row 3 by a negative, and then after that, switch row 2 and row 3. Just in the interest of space and time, I'm going to try to do it in one go, but really you should do that in 2 separate steps. So first, I'm going to do a negative times row 3, replace row 3, right? Then what I want to do is I want to switch. I want row 3 to switch places with row 2. Again, I should do these in 2 separate steps, but I'm just going to try to do it in one. Okay. So with both of these, row 1 stays the same. 1, 0, 2, 1, 0, 0. So now, a negative times row 3, that's going to be my new row 2. So then we're going to have 0, 1, 2, 1, 0, negative 1. And now my row 2 becomes my row 3. So then we have 0, 2, 5, 1, 1, 0. Okay, we're almost there. Okay, so now the goal is to use this 1 to get zeros everywhere else in the column. We're fortunate because we already have a 0 above it, so now we can use that 1 to get a 0 below it. So then what I'm going to do, I'm going to say negative 2 times row 2 plus row 3 replace row 3. Okay, I think I got space to write it here on the side, and I'm going to move this stuff around in just a moment. Okay, so that means that row 1 stays the same. 1, and I could easily I probably should add another page. I don't know why I won't do it. I'm just being silly. 1, 0, 2, 1, 0, 0. Okay. Row 2 stays as is, so that's going to be a 0, 1, 2, 1, 0, negative 1. Now row 3, we said a negative 2 times row 2 plus row 3 replace 3. So that means this is going to stay a 0. This is going to become a 0. Negative 4 plus 5 is a 1. Okay, that's actually really promising. Negative 2 plus 1, negative 1. That stays a 1. 2 plus 0 is a 2. Okay, let me just go ahead and add a page instead of trying to resize this. Okay. Okay. I know why I didn't want to do it, because sometimes trying to add a page, can be kind of a pain. Let's copy, because it takes a sweet time in like registering that I've copied this page. And that's why I keep clicking on it, trying to get it to show my paste option, which it just does not seem like it wants to do. There it is, paste. Okay. And then let me get a copy of where we left off. So you got to be careful with like not giving yourself enough space, because then it gets kind of jammed and crammed, and your chances of making mistakes are increased, when you don't give yourself enough space, right? So that's why I was like, just go ahead and add a page. Okay, so this is where we left off. We're almost there, right? So notice we have a 1 with zeros everywhere else in that column. We have a 1 with zeros everywhere else in that column. We have a 1. Now we want to use that 1 to get zeros everywhere else in the column. Okay, so we can do this. So we'll say it's going to be kind of the same thing, right? We can say a negative 2 times row 3 plus row 2 place row 2. We can also do negative 2 times row 3 plus row 1 replace row 1. Okay, let me actually switch those around. Just change the order. Like, let me replace row 1 first, just because. Okay. All right. So basically we're saying -2 times row 3 and then add it into each row. Okay. So what happens here, let me see. That's going to be what? 0 plus 1 is 1. 0 plus 0 is 0. -2 plus 2 is 0. So then that becomes 2 plus 1 is a 3. -2 plus 0 is -2. -4 plus 0 is -4. Okay. You know what? That's supposed to be, let me back up. No, I think we're good. We're good. We're good. All right. Yeah, I think we're okay. So then now we're changing row 2. Ooh. So then row 2, so we're saying -2 times row 3 plus row 2 replace row 2. So that's gonna stay 0. 0 plus 1 is 1. -2 plus 2 is a 0. 2 plus 1 is 3. -2 plus 0 is -2. -4 plus -1 is -5. Okay. Ooh, come on. And then row 3 stays as is. I gotta get out of the house. Circulation's bad. Okay. So we got 0. So then row 3 stays as is. -1, 1, 2. Okay. So now that we have officially gotten our identity matrix on the left, the claim is that the matrix B on the right is our inverse matrix. So our claim is that A inverse is 3, -2, -4, 3, -2, -5, -1, 1, and 2. Okay. So then we should verify by multiplying A times A inverse. We get identity and switch the order. We need to verify that this is indeed our inverse, like we did in the previous example. I'm just going to use my calculator because I can. Okay. Okay. So there's our matrix A. Let me go back to my matrices. I want to know matrix. How do I delete these? Clear? No, that's what am I doing? Matrix. How do I delete this? So if I go back to matrix. Okay, another thing I can do is just reset the device. Okay, let's go back to matrix. Let's go to edit. So now our matrix A is going to be what, a 3 by 3 square matrix. Okay. And the entries are 1, 0, 2, -1, 2, 3, -1, 2, 3, 1, -1, 0, 1, -1, 0. Okay. All right. So we could just, if I go back to matrix, call on that, and I just hit to the -1, we should get the same thing. All right. 3, -2, -4, 3, -2, -5, -1, 1, and 2. That's good enough for me. All right. So if we were doing this by hand, that would be a pain, right? Because we would need to say A times A inverse, so we would have to do the row times the column, row times the column. We'd have a total of 9 different calculations we'd have to do to confirm that they all work, and they would have to basically ultimately equal the identity, right? But that's why we use technology to keep it breezy. I don't know, I'm just making stuff up. Actually, that came from that movie I was watching. But anyway, right? So then we have a type version. They may or may not do the same thing, but as long as you stick to those row operations, as long as you do those properly, then you'll get to where we left off. I mean, to where we were. I'm liking that this is taking up so many slides. That's getting us through. And I think that's what we got, right? We confirmed that it worked, so I think we're okay. Okay, so hopefully we're all aboard and we're not all bored. If anything isn't clear, feel free to unmute yourself to get my attention or type in the chat and we can talk about it. Otherwise, I'm gonna press on. Oh, and then verify your results by showing the A inverse is I3, and the reverse is also I3, right? So we just used the calculator, but we should have done this, but I was like, it's okay. Okay, so summary: finding multiplicative inverses for invertible matrices. Use a graphing utility with matrix capabilities, or if the matrix is 2 by 2, the inverse of matrix A, this is the formula that we had before. If it's a 2 by 2 matrix, we have this formula we can use, or you can use your graphing utility. If the matrix A is an n by n matrix where n is greater than 2, use the procedure on, I guess, the previous page, where we use the augmented matrix with the in and use row transformations to transform it into INB. Then A inverse is going to be B. All right, so to recap, if we want to find the inverse of a 2 by 2, we can either use this formula or use our graphing utility. If it's larger than a 2 by 2 square matrix, then we use the technique that we just did a moment ago, or you can just use the graphing utility. All right, okay. So let's see. Solve a system of equations using multiplicative inverse of matrix. So the matrix equation is abbreviated AX equals B, right? So we have this coefficient matrix with these A, B's, and C's. We have our variable matrix X, Y, Z, and we have our constant matrix D1, D2, and D3. We abbreviate these three matrices as A times X equals B, where A is the coefficient matrix of the system. X and B are matrices containing one column called column matrices. The matrix B is called the constant matrix. Okay, so we can transform the system of linear equations into this matrix equation like this. Okay, so then if we have the matrix equation AX equal to B has a unique solution, then X equals, so we left multiply. X equals A inverse times B, right? So like, for instance, if this were algebra, if we had some number times our variable X equals some other number we wanted to solve, we would divide both sides by that number, right? But in matrix operations, we don't really have division, right? We don't have division like that. So we wouldn't divide by the matrix A. What we would do is, we would left multiply both sides by A inverse, right? Because remember, the order is important. So to transform this to solve for X, again, we left multiply both sides by A inverse. So then remember, A times A inverse would be identity. Identity times X would just be X. And then on the right-hand side, we would have A inverse times B, okay? So to solve a linear system of equations, multiply A inverse and B to find X, okay? All right, let's keep going. So here we're asked to solve the system by using A inverse, the inverse of the coefficient matrix that was found in the previous example. Let's see. We got 1, 0, 2. Oh, okay. Okay. So we basically they gave us a linear system of equations that matches the matrix A that we had in the previous example. So that way we can use the result that we got to solve this system. All right. Okay. So let's see this in action. First, let's rewrite this linear system as a matrix equation. So first thing we want to do is write out our coefficient matrix. So our coefficient matrix is going to be what? We got X, Y, Z. So it's going to be 1. It's going to be 1, 0, 2. We just want the coefficients -1, 2, 3, 1, -1, and 0. All right. So these are the coefficients. All right. We want to multiply that times our column matrix or our variable matrix, which is going to be X, Y, Z, Z, as they like to say around the world. And then it equals our constant matrix, which is going to be 6, -5, and 6. Okay. So this matrix here is our A. This is our variable matrix X. And this is our constant matrix B. So then if we want to solve for X, X is going to be equal to, if we left multiply both sides by A inverse, it's going to be A inverse times B, right? So then we take that solution that we just found in the previous. I think we got it right here. So then it's going to be 3, -2, -4, 3, -2, 5. -1, 1, and 2. Okay. Times our matrix B, which is going to be 6, -5, and 6. Okay. Okay, we can do this one by hand. So remember, we're always doing the row times the column, right? Can I paste? Is it still there? No. Undo. Right here. So we're going to say this row. Let's try it again. Okay, let's go style. Let's make that thin. Otherwise, it looks good. Okay, let's copy and paste. Okay, and let's go style. Let's make that green. Fill green. Okay. Right. So we say the row times the column. I'm just going to kind of write the solutions. So it's going to be, what is that? 6 times 3. That's going to be what? 18 plus 10 minus 24. That's the first entry. Row times the column. 3 times 6 is 18 plus 10 plus 30. Okay. Again, row times the column. -6 minus 5 plus 12. Okay, so we got 3 results there. So then that's 28 minus 24 is a 4. That's 28. Oh, that's kind of, did I get that right? That's an 18 plus 10 plus 30. Okay, 40. So it's 58. And then -11 plus 12 is a 1. That's so strange to get the result like that. Okay, so when we did it by hand, we got this. Let me confirm this with my calculator. Style. One other thing I want you to notice. So I forgot to mention this earlier, but when we did our multiplication, notice here, A inverse is what, a 3 by 3. The constant matrix, the rows by the column, this is a 3 by 1. Notice that the columns here match the rows here. So that's why we were able to do the multiplication, right? Okay. So we have our A. Let me go here and put in the matrix B. So if I go to matrix, go to edit, and go down to B. B is rows by the column, 3 by 1. So that's a 3 by 1 column matrix. We got 6, -5, and 6. Okay. So then if we do A inverse B, so there's our A inverse, matrix B, we should get 4, 58, and 1. I knew I got something wrong. Let me look at it again, figure out what am I doing wrong with my signs there. 6, -5, and 6. 6 times 3 is 18. That's a positive 10. Did I introduce? Let me check something else. Oh, I'm missing a negative. That's what it was. It was driving me nuts. I was like, that looked like a weird answer. Right here. When I wrote my inverse, I missed my negative right here. So with that negative, that makes that a -30. So I kept pausing. I was like, why does this feel so weird? Right here. So if that's a -30, 28 minus 30 is -2. There we go. That's why we always check whenever possible. So this ends up being -2. Yeah, 4, -2, and 1. Okay, yeah. I was like, yeah, it's driving me nuts. I was like, that's a weird answer. Like, especially for it to be like demonstration purposes. I was like, we don't usually get, not in homework that might happen, or in like real life that might happen. But for this kind of thing, I was like, that didn't seem like my flag was, Spidey sense was tingling. But we got to the bottom of it. When we wrote A inverse, we missed our negative. That one little negative, right? Oh, I forgot to carry the 1, and everything explodes, right? But anyway, we got to the bottom of it. Okay, we're almost done with this section, and we have what, a solid 30 minutes in class left. So let's just keep going. Let's keep going. 4, -2, and 1. So then what we're saying is that when x is 4, y is -2, and z is 1, it makes this solution, this system of equations true. Right? Let's look at the first one. 4 plus 2 is indeed 6. -4 minus 4 is -8. Plus 3 is indeed 5. 4 plus 2 is 6. All right. So this x, y, and z plugged into the original system is the solution. Right. So now you're able to solve a linear system of equations in 3 variables. You are now a genius. Right. I don't know if you know it or not, but you are. Right. So 4, -2, and 1. Okay. So these kind of discussions, what this is like the precursor to this topic in mathematics called linear algebra. Um, Linear algebra is used in like so many different systems, like human systems, economics, a lot of coding, like when they're programming or trying to make plans, like city plans or like street lights, just anything where the people are waiting in line. Anybody that's doing an analysis, like if you, I don't know, if there's a theme park and you're trying to see, okay, is the wait in your park efficient? What's the average wait? How can we maximize this? This comes out a lot in just analysis, like maximizing profit, minimizing costs. It's stuff like this. This is like the beginnings of that subject in math called linear algebra. I'm not gonna lie, when I was in grad school, linear algebra gave me a hard time. This was fun. This was easy. But then in the advanced linear algebra, it was like my mind was like shattered. I was like, what the hell y'all talking about? And it was kind of weird because it was like a mafia. Like, one culture, they just kind of like band together and they took care of each other, but I was like alone. Like I was like the only person like me in all of my classes. So that was really weird. That just was like, okay, I can't take this anymore. I'm good. I'll figure it out on my own. So I was just like, I just let it go. But I mean, but people do it, I just gotta get back on the horse and get back out there and keep trying whenever I want and whenever I'm ready. Okay. I don't really want to do this, but let's do it. Okay, so one application. So this is one application of this topic. This comes out in like cryptography, which is like sending secret message. So like if you're like in the military and you need to send a message to your comrades that are somewhere out in the world, but there's a good chance that your signal or your message could be intercepted. So then you create a hidden code, a coded language to where you would need the key to decipher it. You would want to do it in such a way that if the message were intercepted, it would take them like billions of years. It would take them a long time to decode it by brute force. Like if they had this method for brute force, they're trying to decipher your message. By the time they realize it, the operation, would have been executed, and you're on to a different code, right? There's a movie, I cannot think of the name of it, but there are movies with that very topic. They didn't really do it in Oppenheimer. They didn't showcase it, but there was, and I think it may have been the same actor. I'm not sure, but there was a movie on Netflix. I cannot think of the name of it, but it's some war movie where they're talking about this kind of stuff, cryptography, right? In the war in the military, and them trying to send a coded message, a secure coded message. So a cryptogram is a message written so that no one other than the intended recipient can understand it. To encode a message, we begin by assigning a number to each letter in the alphabet. A is 1, B is 2, so on and so on. Z is 26, and a space is 0. The numerical equivalent of a message is then converted into a matrix. An invertible matrix can be used to convert the matrix into code. The multiplicative inverse of this matrix can be used to decode the matrix. Okay. Okay. So express the word so encoding a word or a message. Express the word or message numerically. List the numbers in step 1 by columns and form a square matrix. List the numbers in step 1 by columns and form a square matrix. If you do not have enough numbers to form a square matrix, put zeros and any remaining spaces in the last column. Select any square invertible matrix called a coding matrix, the same size as the matrix in step 2. Multiply the coding matrix by the square matrix that expresses the message numerically. The resulting matrix is called the coded matrix. Use the numbers by columns from the coded matrix in step 3 to write the encoded message. Okay, that's interesting. So use this coded matrix to encode the word base. Okay, so I think what this is a invertible 2x2 matrix, so we can use this to encode the word base, right? So if we convert the word base into numbers, right? So B should be what, 2? Like it's the second letter in the alphabet. A is 1. So I'm going to do it column-wise. S. Now, I don't know S. Let me think about it. Give me a moment. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. I think that's 19. So I think S is 19. We're going to go with it. And then E, I think it's 5. A, B, C, D, E. Right? That's 5. Okay. So I put those column-wise. Upper left, and then each column. So then we're going to say, so this is where we're trying to get our recipient to. We're going to encode this with our coding matrix. Think about it. Yeah. All right. So then we would say -2, -3, 3, 4. All right. We're going to get another matrix. So if we multiply this, let's see. That's going to be, let me see, if we say the row times the column, -4, I don't know, what was that? 27. I don't feel like doing this. I think I'm going to just use the calculator. Yeah, I'm being lazy. Okay, let's go to matrix. Our first matrix, let's go to edit. It's a 2x2. 2, 19. Hey, Google, what position is the letter S in the alphabet?
According to some
19.
information
Okay.
I found on the
Just
website worldometers.info.
Just making sure.
People also sometimes ask me, what numbers stand for letters? Do you want to hear the answer?
No, thank you. She just be going on to like monologues. Man. Okay, so that's our matrix A, right? So then let's go back and let's edit matrix B. Matrix B is also a 2x2. -2, -3. Nope. Go to -3, 3 and 4. Okay. Okay, let's keep going. So then I'm going to say the matrix A times the matrix B. Can I just recall? Not that one. Did I ever do A times B? No. Okay, I can get rid of this -1. Okay. Okay, so this is the coded matrix. So then we get 53, 70, 13, and 17. Okay, hopefully we did that proper. So then to decode it, you multiply this by A inverse, and then it should get you back to the original, and then you translate it to the word base. Okay. 2, 19, 1, 5. Okay. Now we multiplied on the right. Maybe we should have multiplied on the left. They're gonna get a different result than we got. It just said multiply, it didn't say the order. So I think that when we go to undo it, let me think about this. Decode this. Is that the inverse? Okay. I guess we should maintain the order. I did it out of order. That's why we got a different result. If I just switch the order, we'll get this. So that's why I was like, the order is important, right? I think that we could use what we got. We would just have to, that our recipient would have to know to write multiply by A inverse, right? So let's just see if we multiply, if we write, let's see if that works. Let's just see if that works, right? So let's take that answer and I want to write multiply by A inverse. So I'm going to go to matrix, see if this works. We should get back to our like 219 stuff. Oh, maybe that doesn't work. Wow, maybe we do need to like left multiply because that is not correct. Yeah, wow, that's interesting. Okay. Okay, so I think we do need to hold that order, right? Let's back up. Let's just get rid of this. It's interesting. But yeah, I told you, like the order is important when you're doing these operations. Because in the instructions you just said multiply. It didn't say that it had to be a certain order, but that's fine. So here's our coded matrix. Because this is our invertible matrix, it just needs to be on the left. I think we just multiply like this. Okay. Nope. Okay. So now, let me go back and look at my matrices again. So my matrix A is, that's the second one. Okay, so we need to say B times A. We need to say this times the matrix A. And now we got their result, right? Okay, so we got our, can't write today, -7, -53, 10, and 77, okay? So then to decode it, oh, and so then I think we take it column wise. So then our code would be -7, 10, -53, 77. Okay. So then that would be our code that we would give. Right? It looks like a random string of numbers, right? So anybody that would get that, it wouldn't make any sense without the coding matrix, right? Okay. And you see it here. -7, 10, -53, 77. Okay. That looks good. All right. So then to decode a word, so find the multiplicative inverse of the coding matrix. So we need A inverse. I'm just going to use the calculator there. Multiply the multiplicative inverse of the coding matrix and the coding matrix. And again, I think it should be left multiply. Express the numbers by columns from the matrix in step 2 as, and then from the matrix in step 2 as letters. Okay. So, I mean, basically we would just be undoing what we have. So what we would do, we're going to say, not, we're going to say B inverse. So let me see. It should be B inverse in this case times that answer. And we should get back to where we started, right? And then you take it column wise, all right? So I'm just going to piggyback off of my prepared notes. All right. So we're asked to decode this. So then it's really what we're going to be doing is saying A inverse times this coded matrix, right? So the A inverse is there, the 4, 3, -3, -2. And then for our code, we put those entries column wise. So then -7, 10, -53, 77. When you do the multiplication, you get this 2, 1, 19, 5. You convert those to letters in the alphabet, and you get the word base, right? So just the way to send a coded message. Just something that's fun. Okay. So again, the code there was -7, 10, -53, 77. Anybody that would see that, it wouldn't mean anything to them. The person would have to, have the decoding matrix, the A inverse, in order to decode it. Without that, and even with it, you see, it's still easy to make a mistake if you don't do it proper. But yeah, so that was that one. Okay. We have exactly 15 minutes remaining, and we do have, there's one more section that I'm trying to get through. So we'll hang out for like another 10 minutes. I'll let everyone go in 10 minutes, but I'm probably going to stay on the call to go ahead and finish